let's dive into a little bit more about some of the resources that you would like to share or things that people should keep in mind around how you take a build from like, yes, it physically looks like a build. It's, all the bolts are there to that next level of like, this will last. It's not going to vibrate apart.
This is a perfect lead into that because, like I was just gonna say that, from my one-off experience, I just tend to overbuild things, right? Just make it visually and obviously stout and heavy or strong in whatever aspect you want. So, and that's kind of like how I went about it because I didn't have access or the knowledge to do the analyticals that are required. And uh, when he comes in and he brings in a lot of the structural stresses and yeah, it does take longer. Like, come on, man, we're just building this. Let's just double up on the iron or whatever. And that's not the way to do it. And then he shows me that that works, or what doesn't work, and then you redesign and you go back, and that's the beauty of like using the computers, and that's what's again got me excited to like be involved in that, just because like I said, I would just overbuild it, make it to where it's just obviously bomb proof.
Yeah.
But there's some drawbacks to that, weight design and how repeatability, those kinds of things.
And cost.
But and cost, yeah. If you're building one, that's fine. But if you want to make it something you can put out there and that's reliable and you don't have fear of it coming back, then you go through all the analytics like he does, all the structural sciency stuff that I am learning and enjoying and know about. But like I said, I'm probably more of an intuitive builder. So, but bringing the science in it really like makes you feel secure about what uh, is getting built, you know.
Yeah. And it results in a repeatable thing. The result is a design that's not just robust and manufacturable, but it's also documented. So we have a full set of drawing suites um, that we can just submit to customers, and they can or to our suppliers, and they can do that. They can make it for us. So I'll I have some stuff I can share my screen. Yeah, so this is our, oh, there's some pictures of the solar car race. I don't want to dwell on that too much longer, but there's some cool pictures of it. So yeah, this is our setup here. This is the Nissan Leaf motor, the adapter here in the middle, and the transmission here on the left. So the question is, when we start putting these things together, how do they all survive in what engineering terms we'll call relevant environments? So a relevant environment for us is driving on the street. You got to withstand potholes, curb hits, God forbid, car accidents, things like that.
Hitting fire
So
stations.
yeah, hit slamming
Yeah,
into fire
which it did
stations.
not survive.
So we'll start with things, this is just like a CAD model. You can kind of see the adapter plate that we've developed. On the top is the version that doesn't run a clutch. On the bottom does run a clutch. They're very similar, but they've gone through the same structural analyses. So this slide right here does a good job of explaining, at least at a very high level, what's going on here. So if you can imagine that you've got can you see my cursor when I
Yeah.
move my, okay. So when you've got the motor here, there's a, you learn in engineering school how to do a shear force and bending moment diagram. So if any engineers are listening, you'll probably be familiar with this if you're a mechanical or a civil engineer. So you take something and you assume that it's a beam. And so in this case, you can see this black line. I'm assuming it's a beam. And then you take the center of gravity of each one of the components that's there, and you know approximately where that is, and you know approximately how much these things weigh, and you can put that center of gravity on the beam and then do math to say what are the reaction forces on each one of these things. So for example, this guy right here is the center of gravity approximately. This is not the scale, by the way. This is just what I threw together for state of charge. But this is meant to be the center of gravity for the transmission. This is the center of gravity for the adapter plate. This is the center of gravity for the leaf motor and inverter. Um, And you can plug that into this tool right here, and it'll actually, you can say, you can assign in this tool where all these things are. So you can have a table, and you fill out the table, and I won't go into great detail. I don't want this to turn into a tutorial, but if anybody has questions about this, I can certainly help walk you through this. So you can get a rough estimate of where the point forces are. You'll notice I'm on this point force thing here. You enter in what those are, where their locations are. You hit calculate, and it'll basically give you it'll tell you what all the reaction forces are in this. So what that website gives you is this shear force, that's this, and bending moment diagram. So you can take the shear force and put that into this calculator. So you'll notice this is like a bolted joint. This is like a circular bolted joint. So then this calculator, and these are all free. These links are all for free. So you can assign what your bolt pattern looks like. So in our case, this bolt pattern is what will match the adapter plate bolt pattern. So I would go in here and I would put in XY coordinates for each bolt of our adapter plate. I now know what all the resultant forces are at those locations, and I can put them into this calculator, and it'll tell me what the stresses are in the bolts. So that will help you size, are my bolts big enough? Because you're basically assigning a bolt. You're telling it, in this case, it's a 7/16 bolt. You can change it to whatever you need it to be. So now you can say, are my bolts, at least at this level, strong enough? If you want to go one level further, let's see. Okay. So the first two are a little more high level. I'll admit that. But this one here, you can go through, you can say, what type of joint do I have? A nut with a bolt, and it changes, do you have a nut and a bolt, or do I just have a tap joint? It goes here. You can estimate what these shear loads are, and you can put those in, or you can put those here, and what your tensile loads are, you can put those here. You can make assumptions on this based off of like maybe the weight of the things that you're bolting together. Then you can take the motor and the whole that whole motor and transmission assembly, add it all up, divide it by 3, and you can use those numbers in here for your tensile. You can take those numbers, divide those by however many bolts you have, put those in here. And it is a little more, if you want to do it like perfect, it's a little more complicated than that. But this definitely will give you, a rough order of magnitude. Are you in the ballpark of being good to go or not? You can pick different materials. So the free version just gives you these materials. They're both steels. This material 2 is a higher strength steel, like maybe a grade 8. This material 1 is like a grade 5 bolt. You can pick between inch and metric. So you can pick your different fastener sizes here. I would just leave this preload at 67%. It just means that you load up to 67% of the bolt's tensile strength, which is what you want to do. And then you come down here, you hit calculate, and it'll give you, so let's make up something. Let's say, actually, this is a joint that I was looking at earlier. I think this is actually a M12. So if I have an M12 and I'm putting these tensile and shear loads in, I hit calculate, it'll come over here and it'll tell me the separation. So it gives you separation, bolt yield, and thread shear, or bolt thread shear, and then material thread shear. So what this means is, will the two plates separate? That's this first column. Will they separate? Once a joint separates, it's game over. It's going to break. So this means that you have a factor of safety of 9.3 for nominally, and it's green, so you're good to go. Anything above 1 is positive factor of safety, and you're okay. This bolt yield means that the bolt is going to bend. And we're above 1, so we're okay. The threads on the bolt, will the threads shear, meaning they'll like strip out of the bolt? We're above 1, we're at 2.3. However, because I picked the weaker material that is in the tapped hole, so we're threading a bolt into a tapped hole, I picked the weaker material, so now we're below that. We're at below 1. So there's a risk that we're going to rip the bolt out of the material that we threaded it into. So you might want to consider going either to the next size bigger hole or bigger fastener, or adding more fastener so you can reduce those 900-pound loads that we saw originally up here. 990. This is a lot of force, right? It's almost 1,000 pounds going in tension and shear. So it's a pretty robust joint. So we have to make it a little bit more robust if we want to maintain this size of bolt. So this is just one example of something that this is free. You can go onto this website here, MechaniCalc. And there's a whole bunch of different calculators on here. And you can just make some estimates, some smart estimates about where your system might be. If you have questions about this, whoever's watching this, you can email me, get a hold of me, and I'll help walk you through this. This has nothing to do with me trying to know more than others. There's a lot of people that know this stuff. But if you want to know more and you want to be sure about your builds and understand what you're doing, I'm here. I will help you. This is very meaningful to me. And I said this at State of Charge. If all it's going to take is for one of our conversions to fall apart and hurt somebody, it'll be a major black eye for the EV conversion scene. And I want to do the best I can to help mitigate that. And this is one of my contributions to doing that, in addition to just providing the EV conversion space with parts that we design and proven that have been through all of this. One last thing I want to show you too. So this is a structural analysis program called Ansys Workbench. And so once I go through the motions of proving in all the bolted joints, you can come in here and you can assign all these bolted joints to each one of these things. This is our motor mount, one of our motor mounts. So you can subject it to, this one's seeing 30 Gs of crash load. And you can see all these red spots. Those are areas of high stress. This type of software, I pay for this type of software. However, you can get free versions like Fusion 360. If you have a student version, or if you have a version that's for startups, you can get access to this type of analysis tools. It's a little more advanced. However, it gives you an idea of where your weak points are. And you can even animate it, so you can see it's kind of moving around. Where it'll bend. Yeah. And you can see this force is pulling the motor mount down, so it's secured here and over here.
Wow.
And then it's pulling down, so you can make predictions about where the high stresses are, and then it'll also give you your bolted joint loads if you set the model up right, and you can take those bolted joint loads and put it right into that tool I just showed you that's free. This is definitely advanced engineering stuff right here. These are things that I do at work. And if you set it up wrong, it could give you bad results. However, if your model's very simple and you watch a few YouTube videos like we all do, I think you could have some level of confidence that you can run an analysis, a simple analysis to try to get something going on your end to at least give you an idea. Of course, the other option is just overbuild it. If you're in, and I'm not trying to be facetious, I did that plenty of times.
Yeah.
If you're unsure, just overbuild it and put bigger bolts and more bolts. Yeah. But if you're trying to optimize and you're trying to make it affordable but perform and survive, this is the difference between engineering and fabrication. My son Diego really wants to be an engineer, and he loves to learn about fabrication. You can overbuild things and you can fabricate things to be as big and as strong as you want, and that's always the way to go if you're not 100% sure or you don't have the experience. There are plenty of people that have way more experience than I do building chassis and cars. Don's a good example of this. Like, I'm not trying to say that you have to do it this way. I'm saying that if you want to optimize it, or if you want to understand how things are working and you want to know how things are kind of performing in relevant environments, these are ways you can do it. So you can certainly just overbuild it, and that's the way to go if you're not totally sure. This is the way I do it, and I just wanted to share that with all of you. And if you have questions about it, I'm more than happy to talk to you about it, or even provide levels of consultation just for free. I mean, if you just want me to look at what you're doing and you have questions, I'll do that.